Biswadeep Chatterjee, Associate Vice President at HCLTech, for the second episode of the Chip Chat podcast series hosted by HCLTech Trends and Insights. Today, we're going to be talking about how semiconductors are fueling innovation during the AI revolution. Biswadeep, how are you doing?
Doing great, Nick. Thank you. Thank you for having me here.
Excellent. So just to kick things off, can you give us a brief overview of the relationship between AI and semiconductors, and how crucial is semiconductor technology in driving AI advancements?
Sure. I think in a nutshell, semiconductor and AI have a fantastic symbiotic relationship today. On one hand, semiconductor technologies are driving advancements in AI through newer architecture, newer process technology. We are seeing different new computing style coming up uh, in form of GPU, graphical processors unit, TPU, NPU. We are seeing different type of system architecture being adopted, different software paradigm. On the other hand, it is AI which is driving innovation in the semiconductor industry. And it's not just about smaller transistors, smaller feature size anymore, but it's pushing for adoption of 3D stacking. It is pushing for adoption of different and improved memory technology. So overall, I think both semiconductor is pushing the envelope of AI. Similarly, AI is making us semiconductor VLSI engineers think more about how we can improve the technology itself.
And can you share some of the key breakthroughs that you've seen over the last decade?
Sure. So the first thing that comes to my mind, right, is the use of GPU as part of AI revolution. GPU was originally created for rendering graphics, but its inherent architecture for handling massive parallelization, it makes them ideal for dealing with AI tasks like training deep neural networks. Companies like NVIDIA, which have been in the forefront of optimizing GPUs for AI, with their CUDA cores and introducing features like tensor cores in their Volta and Ampere architectures, right? All of these are pushing the AI envelope. The other ones which come to my mind is TPU, Tensor Processing Unit, which is a specialized ASIC for handling tensor workload, the TensorFlow operations. Then there are other ASICs or application-specific ICs and architecture like NPU, neural engines that are available either on a server class machine, also on handheld, to be able to handle AI workload. So those are the new, I'd say, computing architecture that are coming up. Along with that, you will see newer memory architecture coming up to ensure that we are able to supply the data stream that AI needs to function. AI, as you're aware, Nick, is a data intensive operation, and we need these newer memory architecture, newer interface architecture to be able to feed the engine properly.
Sure. So these GPUs, TPUs, NPUs, they're able to the influx of data to ensure that AI models are able to be trained effectively. Is that right?
Sure. That's right. That's absolutely correct. Trained and inferred, both the training process and the inference process.
So looking at the trend of more devices operating on the edge, such as
Mhm.
in IoT networks, how are semiconductors enabling AI at the edge? What unique challenges do these use cases present?
Sure. So if you look at any edge device, be it for AI processing or otherwise, it comes with certain characteristics. First, it needs to be energy efficient, because when you're operating in edge, you're essentially operating in an energy constrained environment. Second, it has to be, in spite of being very power sensitive, it has to have a very low latency. It needs to respond very fast. And that's the reason it's in the edge. Third, it needs to be able to operate in a situation where the network may not always be very stable, right? And we are seeing a lot of I would say, semiconductor companies which are rising up and addressing this. For example, Apple's neural engine, which is built into its A series and M series, right? It allows AI workloads like image recognition, like natural language processing to be handled directly, but in a power constrained manner. Then NVIDIA's Jetson series, right? That can be fitted even into drones and other autonomous devices. Even Qualcomm's AI engine, which is embedded in its Snapdragon chips, it enhances mobile AI experiences like voice recognition. So we have solutions to this. Similarly, from a data bandwidth perspective, we are seeing much better performance per watt available in the latest memory technologies like HBM, high bandwidth memory. So it addresses the latency concern, it provides a better bandwidth, but in a low power manner. Same for, say, LPDDR, the low power DDR technology that we are seeing, right? It ensures that while it is able to meet the latency requirement, it is at no point kind of eating into the power envelope.
And, energy efficiency, as you've mentioned, it's a key challenge for the rise of AI. It just processes so much electricity. Is there
Sure.
anything else that semiconductor manufacturers are doing to address the need for energy efficient chips, particularly when it comes to AI computing?
Oh, yes, absolutely. And a lot of these are need of the hour today because, as you would have seen, there are already concerns being raised about the power consumption associated with AI. The more data we get, and just as a data point, right? By the time it's 2025, we would be generating 181 zettabytes, right? I mean, these keeps changing from mega, giga, tera, and now we are talking in zettabytes. So the more data comes, the more processing is needed. Now, if the processing pushes the power consumption to an extent where it becomes hazardous for the environment, it would definitely not serve the cause of AI. And that's where low power is something that semiconductor technologists are looking into seriously in terms of coming up with improved technologies like GAA, gate all around, backside power delivery. These are from a core semiconductor technology perspective. We are looking at stacking, doing 3D stacking of chips rather than just growing the real estate, silicon real estate. That way, the delay that is between the power, the data and the compute is contained, which essentially means you're saving on power. The third thing that we are also doing is the first two were more on the hardware side. We are also looking at optimizing and coming up with different form of software operations to be able to conserve or consume less power. And this is very kind of pertinent when we talk about the AI workload. Not all of the AI workload really need 32-bit floating point precision work. So by using technologies like quantization, by using pruning, we are actually bringing down the problem space to more kind of manageable mode where the power consumption is less. So yes, overall the industry recognizes this is a big problem. We understand that unless we address it, we will not be able to continue on this journey for greater and greater AI adoption to the point where we are saying AI everywhere. And we are coming up with solution. I can't say we have conquered the power problem, but we are definitely marching towards it.
So AI is actually helping with the design optimization of processes as well. Can you talk about that in a bit more detail, how AI is influencing the next generation of chips?
Sure, sure. And this is something close to my heart. So, as a silicon design engineer, I've been observing the innovations that are happening in this domain. Uh, to set context here, for the last decade or so, we have kind of been lamenting the productivity gap that exists between the number of transistors that we can manufacture versus the number of transistors that we can design in an appreciable time. And that's happening mainly due to the fact that all the second order and third order effects of semiconductor physics we could ignore earlier. And when I say earlier, say processes like 28 nanometer, 45 nanometer, can no longer be ignored when you're down to 7 nanometer, 5 nanometer, or now we're talking in angstrom units. So it makes the job of an electronic design automation tool, EDA tools as we call it, very complicated. Now, there are two or three things we can do to address that without the AI part. First, we can kind of optimize and start with certain heuristics here. Heuristics like, okay, this rectilinear full flow plan has worked in the past, let's just continue with it. Or what we can do, and which is what we usually do, is we leave a certain guard band. For example, if a technology can push performance up to 3.5 gigahertz, we'll say, let's design the chip at 3 gigahertz. We know we are leaving zero point 0.5 gigahertz on the table, but it assures manufacturability. Now, these are definitely not something that, as design engineers, we are comfortable with, but to ensure that we are able to meet the time to market, these are the decisions we take. With the advent of AI, what we are seeing is we now have a huge repository of data and an ability to infer from those data. For example, now I have information about 1,000, maybe 10,000 or 100,000 designs from which we can infer that a certain power grid architecture is most suitable for a specific product in question. Now, for the designer to do it manually, it was not possible. I can't expect a designer to know what's happening across the industry in 100,000 designs. But now, with AI's ability to train and infer, I not only have this knowledge base, I'm able to decide what to use. Right. And that's what is being applied across the EDA industry. That's where you will see solutions like DSO.ai or Cerberus from Cadence being adopted. So that's one. Second big change that, or I would say innovation that we are seeing is not only can AI help us come up with an optimal architecture, optimal design recipe, it can even go to the extent of predicting defects. Semiconductor geometries, as you know, right? We are talking about now angstrom, and there is very less room for failure. So, in that scenario, we are applying AI to infer saying that, oh, this particular geometry, say a wedge or a L type of a metal strip that we are planning to put, is prone to defect and we should avoid that. Now, for a human engineer to actually go through all these millions, sometimes billions of geometries and figure out which are prone to defect, impossible.
Impossible.
I won't
Yeah.
even use the word difficult. But with AI, we are able to do it. The third one, which is a very interesting case, is in the verification side. And this is not just AI, this is using specifically Gen AI, generative AI's ability to create structured information from unstructured input. It's able to read thousands of pages of data sheets and technical manual and actually convert that into targeted test cases, targeted assertions that can be used for verification. So the verification completeness, which was a complaint for a very long time, is getting addressed in this manner. So I would say AI is helping immensely in advancement of semiconductor. And that's why I started by saying, right, we have a great symbiotic relationship. Newer processors, newer computation technology, newer memory technologies are pushing the envelope of AI. AI in turn is helping us design better, faster chips at a shorter cycle time.
So there's no doubt that AI is booming, the demand for semiconductors is surging. What challenges do you foresee in the industry mitigate these challenges?
I think, and that's what I said, we haven't yet conquered the world. We have set on a very ambitious journey, but there are a lot of things that we need to conquer. For example, I mentioned that we are going to create 181 zettabytes of data, but only a very small fraction of this data is actually getting processed, right? And this is not for a very specific use case. It pervades across all industries. You talk about healthcare, you talk about surveillance, you talk about factory automation. Um, we are surrounded by data collected through sensors, but we are processing only a small percentage of it because of either lack of time or computing power, or network issues, or as I said, the data to computing bandwidth. We need to address that. One way to address that would be to improve scalability in architecture. Yes, today you can pack thousands of CUDA cores, but maybe the need is to go past hundreds of thousands of them without drop in efficiency. And we are seeing startups or newer companies like Fabrica, which is addressing these kind of networking bottleneck. We essentially cannot have a situation where I have a large city and just a two-lane highway connecting to the city. I need 8-lane, 16-lane roadways connecting to be able to solve my transportation, my congestion issues. So that's where we are seeing, as I said, HBM. We are seeing DDR technologies improving, but these are areas that need to be looked into even further. That's one side, that's the engineering side of it. Now, the other part which needs to also be looked into is it's not enough to design improve chips, improve systems. We need to make it manufactured. And I think that's the other challenging part of it is today our manufacturing is also concentrated in specific geographies. We need to go past it, especially when we talk about lower nodes, it's extremely concentrated. We need to go past that. We need to build a global manufacturing hub and not be kind of held hostage by a specific geography. We also need to make our supply chain more resilient. And this was apparent during the COVID days, right? We saw specific countries which were ravaged by this pandemic, right? The moment that supply chain got disrupted, the entire ecosystem almost crashed. So we need to look for resilient supply chain. We need to look for alternate materials at some cases, and material scientists, semiconductor technologists, physicists are working on it. The other part, which also is being looked into related to manufacturing, is all the governments, and not just US, but other governments across the world, have seemed to take cognizance of the fact that we need to globalize manufacturing. So, along with CHIPS Act in US, multiple countries are coming up with their own version of CHIPS Act, their own semiconductor mission, which is giving an impetus to local manufacturing. The last part of challenge which I want to highlight here, And this, Nick, is not just in semiconductor domain, it's across high tech, is availability of skilled resources. Yes, we need to build better chips. Yes, we need to manufacture them. But guess what? Better chips can only be built by better engineers. Even if you have all the possible AI based tools, the final verdict, the final decision making is still dependent on engineers. So we need more and more skilled engineers who can understand the semiconductor physics, and it's becoming more complicated, who can understand the different tools that are needed, processes that are needed, architecture that are needed, and translate them. So to me, these are three things that I think are challenging. And for me, every challenge poses an opportunity. I'm hoping the future generation, the newer companies that are coming up, the startups that are coming up, will focus on these challenges and address them effectively.
Absolutely. Let's hope. I mean, things like the tech skills gap is something that's been going on for decades now across a range of disciplines, not just AI and semiconductors, but everything from cybersecurity to engineering. Now, where do you see the biggest opportunities for semiconductors in AI applications over the next 5 to 10 years? And might we witness a new type of chip than what we have today?
I believe so. In fact, there are four parameters that we look at in semiconductor uh, chips to measure efficiency. We call them PPAT: power, performance, area, and thermal. Now, for area, we have been dependent on this Moore's law. We continue to shrink our transistor feature sizes to keep pace with the Moore's law. But that's more, as it's usually known as. But we cannot all be dependent solely on silicon. And that's where other materials are being looked into seriously to be able to come up. So that's one area. Power, as I mentioned, right, is one of the critical parameters for us to be successful in AI, especially AI on edge. So while there are a lot of these established technologies like dynamic voltage and frequency scaling, DVFS, we have sleep transistors, we put an entire system on sleep, on power down mode when it's not operating. I don't think there also we have reached the zenith of innovation. We need a lot more there. So essentially, it's innovation that will come to push the performance while keeping the power and the area in check. And this is possibly one of the great opportunity that will come to the startups, will come to the future research areas that will happen. The other place where I see a huge opportunity is while it's established now that the traditional von Neumann architecture is not suitable for processing AI, we still have kind of stayed with the classical definition of computing. There's data and there's processor. Now, yes, we are talking now about moving the processor closer to data, moving the data closer to the processor, but still the overall philosophy has not changed. So what we can look at now is newer paradigm completely of computing. For example, neuromorphic computing. Neuromorphic chips, which are designed to mimic the brain's neural architecture using, say, spiking neural networks that can process the data asynchronously and in parallel, right? These will help drastically lower power consumption. Then we are talking about bio-inspired learning. Learning which would excel in applications that require real-time pattern recognition real-time sensory processing, and be useful in the cases like robotics, in prosthetics, and autonomous systems. The third opportunity that I see is in the software side. Because it's not enough from a hardware to be able to get power optimized hardware. We need to optimize our software architecture, our software operations, also to be able to kind of keep the power gains that we are getting in hardware intact. And that's where we need to look at, say, some of the things like data pruning, data quantization, uh, being able to reduce the number of operations and reduce also the accuracy of these operations to be able to gain the same power, that the same advantage that is being available from hardware side. For example, can we look at a more improved version of TinyML and have it on a handheld device to be able to make quicker, faster decisions in a very power efficient manner? So I think these are some of the domains that we would need to address in future.
Sure, lots of opportunities ahead. And just finally, Biswadeep, what advice would you give to companies looking to stay ahead in the dynamic industry of AI and semiconductors?
I think the first thing to look at is do not remain in a me too bucket. Yes, there are the undisputed, as of today at least, undisputed leaders of AI who have established certain paradigm, the NVIDIAs of the world, the Googles of the world. But improving what NVIDIA has done, improving what a tensor processing unit is not going to give them the winning edge. We would need to look radically in a different way because AI is a nascent industry still. Yes, we have thought through the solution in a specific way, but no one can claim that this is the only way to process AI. So we would have to look at, so for example, custom AI accelerators, edge devices, which can actually be more power efficient using a totally different architecture. We have already uh, done 3D stacking. Is there even better way of coming up with a chiplet architecture? Now, one thing you will notice, Nick, is I'm still using the familiar terms. I'm saying chiplet. I'm saying 3D stacking. The reason is possibly we don't even know what these new terminologies will come up. For example, right, can we embed AI into the sensor itself? Today, what happens is the sensors trap information, send it to AI devices, maybe at the edge, and wait for certain actuation. Can we embed these AI engines, these tiny engines, into the sensor itself to be able to locally sense, infer, and actuate? It's not enough to just infer. You have to actuate something there. So these are some of the things that I would say uh, that the AI industry or the industry in general needs to look forward to.
Sure. There's lots on the horizon, but it's a bit of a watch this space conclusion and see what innovations are on the horizon. Biswadeep, thank you so much for your time, and thank you to the audience for tuning in as always.
Thank you so much. Thanks for such a great discussion, Nick.